Okay, we are going to look now at electron arrangement. We've previously been discussing elements, protons, neutrons, and electrons. They're subatomic particles. Now we're going to examine their behavior. So let's look at lithium, sodium, and potassium. And we're going to look at lithium 7, sodium 23, and potassium 39. It turns out that lithium, sodium, and potassium all behave in a similar fashion. It's like they're in a family. You know how you have similar traits to your family members, even though you might not want to admit it, but it's there. The same can be said of lithium, sodium, and potassium. So let's try to figure out why they behave in a similar manner. So let's see. Lithium, how many protons does it have? Well, lithium is atomic number 3, so it's going to have 3 protons and 3 electrons. And I've given you the mass number, so the number of neutrons is going to be 7 minus 3, or 4 neutrons. Let's look at sodium now. Sodium has an atomic number of 11, so the number of protons and electrons are going to be 11. The number of neutrons is going to be 23 minus 11. So that would give you 12 neutrons. And then potassium has an atomic number of 19, so 19 protons, 19 electrons. 39 minus 19 is going to give you 20. So just looking at the number of protons, the number of neutrons, and the number of electrons amongst all these, it does not seem like they have anything in common. So why do they behave the same way? Well, it turns out that it has to do with their electron arrangement. So not all electrons are located in the same orbit around the nucleus. There's a specific arrangement for the electrons. The orbits are also referred to as shells, since they are three-dimensional, or sometimes they're referred to as energy levels. So the orbit or shell closest to the nucleus has the lowest potential energy. The negative electrons are closest to the positive nucleus. The shell closest to the nucleus is also the smallest, so it can hold the least number of electrons. As orbits move farther away from the nucleus, they are higher in energy, not as close to the positive nucleus, and they are larger in size. So experimentally, this is just kind of information for you, not that you need to memorize everything I'm saying, but it maybe will help those of you who want to understand more. So experimentally, these orbits can be observed when electrons jump from one orbit to the other. So adding energy to an electron in a low orbit causes it to move to a higher energy orbit, further away from the nucleus. This energy can be supplied by electricity or heat. An electron in a high energy orbit will try to jump to a lower energy orbit if there is room in the lower energy orbit. And in doing so, it must give off energy. The energy is given off in the form of visible light. So we see this with neon lights. So a neon light gets energy from electricity. The electrical energy is absorbed by the electrons in the neon atoms. And as they jump to higher levels, they quickly fall back down to the original lower energy level and emit energy as visible light. So that's the orange-red. So Niels Bohr developed a model of the atom where electrons were confined to specific orbits, energy level, at different energy levels. This is referred to as the quantum theory. The energy levels are quantized rather than continuous. This means that electrons can only exist in specific orbits that have a specific energy. Not all energies are possible, and electrons cannot remain stuck between orbits. For example, stairs or floors of a building are quantized. A person must stand on one stair or the next. It is not possible to be standing on stair 1.5, for example. You're either standing on stair 1 or stair 2. Bohr was able to predict the wavelength of the light to 10 decimal places, and experiments showed him to be exactly correct. This led to the acceptance of the quantum theory of the atom. So, electrons are arranged in shells or energy levels around the nucleus. So it's almost like parking places, kind of like a parking structure. You know, when you first go in, the first shell of spaces available to you is like the lowest energy. Your car has to drive the least amount. Then you go to the second level and the third level. And usually there are less spots in the lower one. So, you know, so you think of that analogy. So the first shell holds a maximum of 2 electrons. The second shell, or level, holds, it's slightly larger, it holds a maximum of 8 electrons. The third shell holds a maximum of 18 electrons, and I have 8 written here. And then the fourth shell holds a maximum of 32 electrons. For our course, we just keep these maximums in line because we are not going to go above atomic number 20 when coming up with electron arrangements. So if you go on to a higher level chemistry course, you might hear 18 electrons max here and 32 electron max here. But for our purposes, we're just going to stick to this. So electrons will fill shell starting with the lowest energy shell. Once it is full, it starts filling up the next higher energy level. The electron arrangement is important to understand since the electrons determine the chemistry of an element. If you know the electron arrangement, you can predict the chemical behavior. So what we didn't do here is look at how the electrons are arranged. So based on what we looked at from lithium, sodium, and potassium, we shouldn't expect to understand anything more. We need to look at how these electrons are parked in their parking spaces. Okay, so let's do this first. On the next page, we'll copy the number of electrons from this page. So 3, 11, and 19. Okay. We're going to park these electrons and figure this out once and for all. So lithium has 3 electrons. It's going to park 2 electrons in shell 1 and 1 electron in shell 2. Sodium has 11 electrons. So it's going to park a maximum of 2 in shell 1, a maximum of 8 in shell 2, and then it has 1 left over to park in shell 3. Potassium has 19 electrons. So it's going to park 2 electrons in shell 1, 8 electrons in shell 2, and so that takes care of 10. Another 8 electrons in shell 3, and then it has 1 left over for shell 4. Now, do you notice a trend? Yes, I see it. Look, the outermost shell of lithium, sodium, and potassium all have 1 electron in it. So that's why they're in the same group and they behave the same way. So lithium, sodium, potassium all have 1 electron in outermost shell. Okay, so let's park these electrons for hydrogen, nitrogen, chlorine, and calcium. So hydrogen has 1 electron. It's just going to park 1 electron in shell 1. All right, nitrogen, when I look on the periodic table, has an atomic number of 7. So 7, so I'm going to park 2 here and then 5 here. Chlorine has an atomic number of, there you are, chlorine, 17. So it's going to be 2, 8, 7. And then calcium is over here, 20. So it's going to be 2, 8, 8, 2. So this brings us to the periodic law. Elements in the same group behave in a similar fashion due to electron arrangement. Okay, and this is kind of a summary of what I was discussing. Electrons can absorb energy. When energy is absorbed, electrons jump to a higher shell. When electrons fall from higher energy levels to lower energy levels, energy is given up, often in the form of light. So think about fireworks. So pretty neat when you think about all the different chemistry that's around you. As much as many people would say, yeah, I don't need chemistry. Chemistry is not around me. It's everywhere. Okay, so energy is given off in the form of electromagnetic radiation. Radiation can be characterized by frequency and wavelength. Okay. So moving on, I want you to hit pause and figure out the electron arrangement for the following elements. Now, it could be that in your high school chemistry course, or maybe you've taken a higher level chemistry course, you talked about 1s2, 2s2, 3s2, 3p6, all of these. We don't get into that in this course. We keep it simple. So I want you to figure out how many electrons these elements have and park them according to the simplified electron parking that we do in this course. So hit pause and then come back and we'll go over the answers. Okay, so hopefully you got these electron arrangements. For sulfur, 286, silicon, 284, beryllium, 22, aluminum, 283, and argon, 288. So we are going to talk about radiation now. So Röntgen discovered X-rays accidentally while doing research on cathode rays. He noticed that a screen on the other side of the room was glowing, even though the cathode ray tube was surrounded by black paper and was pointed away from the screen. He was apparently quite shocked when he discovered that he could see his bones in his hand through the flesh. In Europe, X-rays are called Röntgen rays in his honor. Okay, so Becquerel, and this is misspelled, it should be B instead of V. Becquerel discovered radioactivity accidentally when a rock placed on some photographic plates inside a drawer caused them to be exposed. He realized the rays given off by the rock were more powerful than X-rays. So, discovered radioactivity accidentally when a radioactive rock exposed his film. Okay, and then Marie Curie studied radioactivity and isolated many radioactive elements. So she studied radioactivity and isolated many radioactive elements. She was born in Poland, but due to the political situation was forced to leave and immigrated to France. She studied at the Sorbonne, one of the few women to do so, and was allowed to work in an unused part of the laboratory. She married Pierre Curie, and they studied radioactive elements and carried out chemical separations to isolate them. She and her husband won the Nobel Prize in Physics in 1903. After her husband's death, she continued to work on radioactive elements and won the Nobel Prize in Chemistry in 1911. She was not elected to the French Academy of Sciences because she was a woman. So, we're going to talk more specifically about radioactivity now. So Rutherford, remember him? We talked about him when we were talking about subatomic particles. So Rutherford was able to differentiate three types of radioactivity. So alpha has a charge of +2, mass of 4. It's slow moving, not very penetrating. It's the same as a helium nucleus. So you can see an alpha particle abbreviation written like this, or this. Okay, beta has a charge of -1. Negligible mass. It's the same as an electron. It moves faster than an alpha particle and can penetrate the skin. So the abbreviation for this is beta, or same as an electron. Lastly, gamma has no charge, no mass. High energy form of radiation, higher energy than X-rays. And this is the same as cosmic rays. Can penetrate very deeply and causes substantial damage to cells. This is used for cancer treatment, so this is radiation treatment. Okay, so gamma 0, 0. It's kind of like a fish standing on its head, legs. Okay, so that brings us to background radiation. So we are all exposed to small amounts of radiation every day from natural sources such as rocks, water, air, sunlight, as well as man-made sources such as TV sets and X-ray machines. The amount of radiation is very small, and most of your exposure is from the materials making up the concrete in buildings. So, small amount of radiation from natural and man-made sources. Okay, so this gives you an idea of the different radiation levels. So radiation, such as X-rays, has enough energy to knock an electron completely out of an atom. The particle that remains has a net charge. So that's an ion equals a charged particle. It's not only a car. So an ion, put this, charged. Okay. We will see in later chapters that electrons will pair to form stable chemical bonds. When the radiation removes an electron, the remaining particle has an unpaired electron. This is called a free radical. Free radicals and ions are highly reactive and can damage other structures in the cell. There are many units to measure radiation. A common unit is a rem. So rem is the radiation equivalent for man. R-E-M. You can use the following information to estimate your exposure to radiation. So, smoke detectors, clocks, food, house construction, stone, concrete, masonry. So if you hear, if you ever buy a house, you have to get a radon mitigation system. That has to do with radiation that's being emitted from the minerals in the foundation of your basement. So, you know, when you go through home inspection. That's one thing that you do look at when they measure the radioactivity. If they find it's above a certain level, then in order to sell the house, you have to have radon mitigation put in. And it's a good thing. You don't want to be exposed to radioactivity. Okay, so I think this got cut off. So usually the U.S. average dose is about 180 millirem per year. And I think these are in units of, make sure. Shame on me for not, these are all millirems. Okay. So the U.S. average dose is 180 millirems per year. A lethal dose is about 500 rems. So that would be 500,000 millirems. So this background radiation that we're exposed to is very minimal. But if you work with X-rays, maybe you work in the medical field, or if you see somebody, you know somebody who works in the medical field, you'll notice that they have a film that they wear. It's kind of like a badge that they wear. And on a weekly or monthly basis, they submit these films to be examined to see how much radiation they've been exposed to. And if they've been exposed to too much radiation based on this film, because the film exposure tells them how much they've been exposed to, then they might not be able to carry out X-rays. I used to work in a pharmaceutical company where we made radio-labeled pharmaceuticals. It was like a custom lab that if you wanted a radio-labeled anything, you could call and ask us to make it. We'd make it for you. But we worked with radioactive chemicals. And so we had to take urinalysis tests every week. And our radiation exposure was measured through our urine. And if it was above a certain level, we weren't able to work in the lab. And, occasionally somebody would spill a chemical and they would be exposed to a lot of radiation. And so, I'm sorry, you're not going to be able to work in the lab. You're going to have to do some paperwork for the next month. They just kept monitoring them. So it is something that you have to be careful with. Radiation, ways to protect yourself from radiation. There are measures that you can use, and I definitely used this when I was working. So time, the less time you're exposed means less radiation. So if you decrease the time, you decrease exposure. The distance, the greater distance means less radiation. So if you increase the distance from the source, you decrease exposure. Shielding, a physical barrier to stop radiation. So this is what I did. Like I wore gloves, I wore a Tyvek suit. So paper, clothing, and skin provide shielding against alpha particles. So alpha, paper, clothing, and skin. Beta, you need wood or heavy clothing. Gamma would be lead or concrete is needed. Lead or concrete. And this is lead or concrete several inches thick. It's not just a thin. So the heavier particles are less penetrating than the lighter particles. So remember, alpha is heavier. Beta is a little lighter, and gamma is the lightest. Alpha particles are stopped by the outer layer of skin. Beta particles penetrate a few inches, but in general do not reach vital organs. Gamma radiation can pass through the body, so it is the most dangerous. So in the next lecture, we'll talk about types of radioactive decay and we'll work problems with them. So practice your electron arrangement and go over your definitions. Do your homework problems now. That will help you.